Hello, my name's Leo Peach. I'm a PhD candidate from Griffith University, and today I'm going to talk about investigating machine learning for virtual wave monitoring. First of all, a brief introduction. So, why do we want to know about waves? Waves and understanding wave conditions and monitoring them is important for activities such as fishing, boating and surfing, but also commercial activities like shipping and maritime transport, and increasingly offshore renewables. It's also important for things like disaster management and beach management. So what's our aims and objectives? We're looking to understand what machine learning can do to supplement the existing wave monitoring network. Can it be used to fill gaps in long-term records? And can it be used to extend beyond the existing data that we already have? So let's have a look at the location and the available data. We looked at an area on the east coast of Australia because we wanted to look in this region. We used datasets from 4 reasonably close wave buoy sites operated by Queensland and New South Wales governments. 2 that are in deeper water, 80 and 60 meters respectively, and 2 in shallow water in near shore areas. You'll also see on the map several red dots, and those are the locations of some short-term wave monitoring sites, which we'll talk a bit more about a bit later. We had approximately 19 years of data between 2000 and 2019, but once we included all of the overlaps and conducted data cleaning and quality control, removing any obvious errors, we had approximately 17 years of hourly observations of wave parameters. So we had a look at the literature, and typically wave monitoring networks have been supplemented by wave models, such as spectral wave models. Research for machine learning in terms of waves has really focused on wave forecasting, and a variety of techniques have been used to estimate wave parameters here. Some techniques have also used machine learning and latterly deep learning to reconstruct wave parameters between wave buoys. But really, we're focused on this region, as most research has looked at elsewhere, to see if it's applicable here. And again, our focus is very much around understanding and trying to map wave parameters from offshore locations to nearshore locations. Let's have a look at the method. Wave climate analysis was an important initial step. What we really wanted to understand was, are the wave monitoring sites close enough that we can potentially form a relationship? And also we really wanted to understand what the similarities and differences were between offshore and nearshore wave monitoring locations. So if you look at the plot on the right hand side, we've got distributions of 4 different wave parameters that we looked at, and you can see, so say for example looking at direction, there's a difference between Byron Bay and Brisbane, which are in blue and orange respectively, and the green, which is a nearshore wave monitoring site of Tweed Heads. In this case, we're trying to map our source location or our source features in terms of machine learning jargon to our target location, which is our labels. And the way that we've looked at our model configuration is we have 5 wave parameters from our source locations from each one, and they are mapped to a single target or label, which is a single parameter at the nearshore or target location. Data preparation for encoding the data, particularly direction, was important, and we also undertook scaling. 6 months of data was also kept completely independent, and that was for validation purposes. So when we look at model development, we undertook time-series cross validation. This serves two key purposes. The first is to identify and to tune the model parameters. We need to find the best ones to get the best performing model. And the second is because we're looking at time series, we want to consider those together. We don't want to break them apart. And so we want to consider seasonality. So in this case, we looked at 3 months for our training period and then 2 weeks for our testing period. And the way this works for our 17 years of data is that the first training is undertaken for 3 months and testing for 2 weeks, and then another 3 months is added, and so on until the complete data set is exhausted. We'll use two techniques. Both have been used extensively in the literature. The Multilayer Perceptron approach, which is a neural network, an example or a simplified example is on the right hand side of the slide, and the random forest decision tree approach. So let's take a look at the results. So the first wave parameter we're going to look at is significant wave height. And here we're assessing its performance against that independent data set that I mentioned, which is a 6-month period in early 2019. And it is inclusive of some storm conditions from tropical cyclone Omar, which was off the coast at the time. You can see in the plot, or the time series plot, on the bottom left hand side, the observations are in blue, the multi-layer perceptron is in yellow, and the random forest in green. Now we wanted to focus on the overall performance, and the performance metrics table can be seen on the right, and the performance during storm conditions as well, because it's possible that particular users may be interested in those sorts of conditions and the performance of such predictions during those periods. And you can see in this case, there's slightly poorer performance in storm conditions than the overall performance. Taking a look at mean wave period now, very similar plots, but I'll just cast your attention to the performance of the multi-layer perceptron model and the random forest model for storm conditions, as mean wave period actually performed better during storm conditions. Let's have a look at peak wave direction now. So peak wave direction is perhaps a more unstable parameter than the two parameters that we've just looked at, and therefore is a bit more challenging to create predictions for. So you can see that that's reflected in terms of the skill metrics, where overall so far it's the worst performing parameter in terms of predictions. There's also another potential reason for this. So if we look at the plot along the bottom, I'm just going to highlight an area here. And so although in terms of the cross-validation we included a 3-month period, it's possible that this is not granular enough for more rapid changes in direction associated with changes in peak period. And you can see that the observations in blue change direction at a different time to the machine learning predictions. So let's have a look at the overall performance then. For the machine learning predictions, significant wave height performed the best, and you can see that in red in the Taylor diagram on the right hand side of the slide. Mean wave period was the next best performing, and interestingly performed better during storm conditions, and the worst performing was peak wave direction. So let's have a look at some potential applications. So here's an example for a virtual buoy site at Belinga. So what we're doing here is we're trying to extend one of those short-term wave monitoring sites that I mentioned at the beginning of the presentation. You'll see from the map in the bottom right that it's located pretty close to the Tweed Heads wave monitoring site. However, there are some significant differences. The original available data period, which you can see in the time series plot here, is much shorter than the training period that we used previously, less than 10 months. Therefore, for cross-validation, we reduced our training period down to 3 days. However, you can see when compared to the Tweed Heads observation in blue in the time series plot, the Multilayer Perceptron in orange and the random forest in green seem to trend pretty close to one another. Let's talk about the results in a little more detail though. So let's look at the scatter plots now at the bottom of the slide. You can see the observed HS from Tweed Heads on the x-axis and the HS predicted from the Multilayer Perceptron model and random forest models. There's an important point here. You can see this feature in the random forest significant wave height predictions. And this is because the random forest approach has a limitation. It cannot incorporate wave heights, or in this case, wave heights in meters, outside of the original training range of the data that it was provided. So this is an important consideration for this type of application. Conclusions and discussion. So what are the benefits of this kind of approach? They can be applied even if no other information is available, so aren't reliant on bathymetric information or wind and offshore wave conditions, like many physics-based models such as spectral wave models. But they do need to have several close proximity wave monitoring sites with reasonable overlapping datasets. The machine learning models are a bit of a black box. You don't really understand what they're doing. And this approach requires several different machine learning models for each wave parameter you'd like to predict. And some approaches can only predict within the range of training values, and therefore which one is applied should be considered carefully. However, they're relatively quick and cheap to develop. So some further research and extensions to the work that we've already done. We'd really like to focus on techniques for improving things like wave direction and the performance of particular scenarios or sets of conditions that might be of interest to a particular user, such as storm conditions. And we also would like to look at the dependence of time as a parameter in more detail. And we think perhaps something like a recurrent neural network would be able to help with this. Here's some of the main references. Thank you for listening.